This video is on simplifying radical expressions. We are going to be simplifying radical expressions. The expressions means we're going to have both numbers and letters, or it could just still be just numbers or just letters, but an expression means that we could have more than just numbers. So before we even begin simplifying them, we need to understand what all is inside of a radical expression. We have four different things here. This first thing, this is y times the radical. This y represents the coefficient of the radical. This y is multiplied to the radical, so when you simplify it, whenever you bring something out of the radical, it is something times the radical. The next part we're going to look at is this b part. This b is inside this nook. It is not attached to the y. It is attached to the radical itself. This b part is called the index. Now, the one thing you need to know about the index is that it needs to be greater than or equal to 2. Because the smallest type of radical you can have is a square root. There is no 1th root, but it needs to be greater than or equal to 2. If it is a 2, you actually generally will not see anything written here because that is the normal radical is just a square root. So if you don't see a number written there, you know it's just a 2. If it is anything other than a square root, the index must be written. The next thing we're going to look at is the part that's inside the radical itself. We have an x and an a. The x is the radicand. The radicand is the part that is inside the radical. That is the part that we're going to try and simplify. That is called the radicand. The last part, our a, if you can see that it's x raised to the a power, the a represents the exponent of the radicand. And what we want to try and do is, if we could potentially simplify the exponent, because we want to try and get as much out of the radical as we can. So if our exponent is bigger than our index, that means that we will be able to simplify it further. What we're going to do first is we're going to do some simplify radical examples. We're going to have no decimals. We're going to simplify just these values by using our perfect squares or cubes or fourths, whichever ones we're dealing with. This first problem is the square root of 28. Because there is no number inside of our index, it's an automatic 2, so this is the square root of 28. If we remember back from just simplifying radicals, we look for the largest perfect square that goes into 28. This could be rewritten as the square root of 4 times the square root of 7. The reason we want to do this is because the square root of 4 actually simplifies. It does not become the square root of anything. It actually simplifies down to a final number. The square root of 4 is 2. That becomes our coefficient. Times the square root of 7 will not simplify any further, so we have the square root of 7. Now the index would also be a 2, but since it is a 2, we do not have to write it. Our radicand, remaining radicand, is 7, and the exponent on our radicand is a 1. Now because it was 2, the index is bigger than the exponent. That tells us that the expression shouldn't be able to simplify further. So this would be our final answer. Our answer is, we would pronounce this as 2 square root of 7. This next problem, the square root of 80, also is a square root because there's no number inside the index. We want to find the largest perfect square that goes into 80. This can be rewritten as the square root of 16 times the square root of 5. Because 16 is the largest perfect square that goes into 80. And 5 times 16 is equal to 80. This square root of 16 will simplify to an integer, to a whole number, not another radical. The square root of 16 is just 4. So our coefficient is 4. The square root of 5 cannot simplify further. So it's going to be 4 times the square root of 5. This is our final answer for that one. On this last example of just simplifying radicals, we have 2 times the square root of 243. Now our coefficient is already a 2, but that doesn't mean that that will be the only coefficient. We got to remember that anytime we simplify a radical and we bring out another coefficient, it will multiply to the one that's already out there. So we can actually keep this 2 out on the outside. This is 2 times. And now we want to actually simplify the square root of 243. So the square root of 243, just this part, can be rewritten as the square root of 81 times the square root of 3. Now the square root of 81 simplifies to be 9, so it's going to be 2 times, because our new coefficient for the square root of 81 is 9. It's 2 times 9. And then we're going to still have the square root of 3. We have our index of 2, and we have our radicand of 3. Now, because we have 2 coefficients on the outside, we do want to multiply those. So 2 times 9 is 18. So our answer is going to be 18 as a coefficient. And then we'll still be left with the square root of 3. And you can check in your calculator to see if you get the same decimal value. We don't want decimals in our answers, but we can always check to make sure our decimal values are equivalent, because that's all we're doing is rewriting the problem to make it look different, but we are not changing the value. So if I take my calculator and I type in 2 square root 243, so 2, then the square root of 243, I press enter, I get 31 and 1800ths. Now I'm going to type in 18 square root of 3. I'm not going to clear this. I'm just going to put 18 square root of 3. And I do get the same decimal value. That means that I know that I'm on the right track. 3 is prime, so I know that I cannot simplify that radical any further. So I know that this is, in fact, the simplified version. On this video, I'm also going to explain how to simplify letters as well. So simplifying radical expressions, this is just letters on this one. In a separate video, I'm going to combine numbers and letters. So here, I'm just going to explain how to simplify the radical expressions with letters. There are multiple ways to do this. What you're really trying to figure out is how many sets of the perfect squares or cubes or fourths can go into this problem. So on this problem, we have the square root, so this index is a 2, of x cubed, y to the 7th, and z to the 6th. As I stated earlier, the exponent, if the exponent is bigger than the index, that can be simplified. So we can simplify the square root of x cubed. As we were doing up here, we wanted to find the perfect squares, the largest perfect squares that go into the problem. The largest perfect square that goes into x cubed would be x squared. And then we would also have y to the 7th, z to the 6th. We need to simplify those. So you always want to check to see, is your index smaller than the exponent? Or, as I said earlier, the exponent is bigger than the index, whichever one. So we have a 2 is smaller than 3, x's will simplify. 2 is smaller than 7, y's will simplify. 2 is smaller than 6, z's will simplify. The way I like to show this, and again there are multiple ways of doing this, I write out my different letters. I have an x, I have a y, and I have a z, and I do know that these will simplify. Because we are figuring out the biggest perfect square that goes into this, because this is a square root, we really want to know how many perfect squares can x cubed have. How many perfect squares can y to the 7th have? How many perfect squares can z to the 6th have? What you really do when you're working with exponents is, if I want to get to the perfect square, I need to divide out how many perfect squares there are. So instead of me writing out x 3 different times, y 7 different times, and figuring out how many pairs there are, instead I take my index, because it's smaller than my exponent. My index is 2 for the x's, and I see how many times that index can go into my exponent of 3. This is for the x's. So when I do this for the y's, I will still keep my index of 2, and I want to know how many times it will go into the exponent of 7, because this is for my y's. For the z's, my index is 2. I want to know how many times it goes into the exponent of the 6 for the z. The reason that we can do this is our actual answer we get will be the new exponent on our coefficient, and the remainder will be the exponent on our radicand. So 2 goes into 3 one time. We can use 2 one time, but then there's going to be 1 left over. This goes back to just basic long division. This will be 1 times 2 is 2. You would subtract it from the 3, you'd be left with the 1. If we do this one, 2 goes into 7 3 times, because 3 times 2 is 6, and we'd also have 1 left over. On the z's, 2 goes into 6 3 times, with the remainder of 0. Now again, the reason we're doing this is because this will actually tell us the exponent. These are all exponents. This is an index and an exponent. So this has not just become a coefficient of 1. This is the exponent on the coefficient for the x's. This is the exponent on the coefficient of the y's. So this turns out to be, since I'm dealing with x's, this is the exponent of the coefficient. So this will be x to the first power. That's the coefficient because it's outside the radical, because I was able to go evenly into 3. But then I do have a remainder. Since I have a remainder, I have to have a radicand. This is the exponent of the x in the radicand. So I have to have the square root again. I know it's a square root because my index was 2. I'll still have an x left over, but my exponent of that will become a 1. For the y's, I was able to divide it evenly. So I have my coefficient of y. This is the exponent of my coefficient, so this will become y to the third. I do have a remaining exponent. That means that I have to have a radicand. So I need to have my square root symbol again. And again, it's a square root because my index was 2. Now, since I have a remainder, I have to have a radicand of y. And this is the exponent of my radicand. This is a 1. For the z's, I see that I went into it evenly, so this is the exponent of my coefficient of z. So I put my z with the exponent of 3. I have 0 remaining. What that means is that I will not have a radicand left over for the z's. So what we've just done is we've simplified each individual part of it, and now we just want to put it back together into one final answer. So you want to find all of your coefficients first. So I have no numbers. I've not simplified numbers like I did up in these first 3. I'm just simplifying the letters. So on these, I want to find all of my coefficients, anything that's outside of the radical. I have an x to the first. I have a y to the third. And I have a z to the third. Now we need to do our radicands, which means we're going to have radicals. So because I have a radicand in at least one of them, I know I have to have a square root symbol again. It has to be a square root because I have to keep it square root to square root. My radicands are, I have an x for the first one, an x to the first. I have a y to the first. But then I have no radicand left for the z. So then this would be my final answer. I have all my coefficients together, and I have all of my radicands together underneath the same radical we started with. So again, we're trying to figure out how to simplify all of these exponents. If I go to example 2, this time I'm still only dealing with letters, so I have A, B, and C. But this time we're dealing with a cubed root. So again, we want to see, is our index smaller than our exponent? So our 3 is smaller than the 5. That means A's will simplify. I will be able to have a coefficient of an A. 3 is smaller than 9, so I will have a coefficient of a B, some type of B. 3 is not smaller than a 1. So I know that C's will not simplify. I will not be able to simplify this at all. So I still want to write out all 3 of my letters. So I have A, B, and C. For my A's, I start with my index of 3, and I want to know how many times 3 can go into the exponent of 5. For the B's, I want to know how many times the index of 3 can go into the exponent of 9. And for the C's, I know that the C's will not simplify because the index is too big, but I'm still going to show the process of this. So I would still see how many times does 3 go into the into the exponent of 1. So if I were to simplify this, 3 goes into 5 for the A's 1 time, but I know that there's still going to be 2 left over because 3, I need 5 to get to 5, so I need 2 more. 3 for the B's, 3 goes into 9 3 times with a remainder of 0 because it goes into there perfectly 3 times. For the C's, 3 does not go into 1, so I need to put a 0 with the remainder of, because 0 times 3 is 0, if I were to subtract this, I would still have the remainder of 1. What this means, because I knew that 3 is too big for the 1, I knew that this would not simplify at all. I would have to keep the C to the first power as my radicand, and this proves that that would happen. My radicand exponent is still going to be the 1. So now I'm going to write the individual ones out. For the A's, this tells us the exponent of our coefficient of A. So I have A to the first. We still have a cubed root because this tells us we have a remainder. I need to put a radical. The cubed root of, we have a radicand of A with the exponent of 2 inside your radicand. For the B's, I have the coefficient of B with an exponent of 3. But I do not have a radicand exponent, so therefore I don't need to put a radical on my B's. For the C's, I do not have an exponent for our coefficient, so I do not have a coefficient of C's, but I do have a radicand exponent, so I still need to keep my cubed root. I need to have the letter C for the radicand, and the exponent is that 1. So as we said, the cubed root and the C to the first will not simplify, so the C to the first will stay in there as it was. So we did not have to do this part because we knew that this would not simplify. But this is the reason why. This is the process of that. So to put all of our parts together, I want to get all of the coefficients, so everything on the outside of the radical. We have an A to the first as 1 coefficient. We have B to the third as 1 coefficient. And then the C's, there are no coefficients. So now we have to go back to our radicals. We do have radicals, so I need a cubed root. I need to be careful when I write that cubed root to make sure it is inside the index and not attached to a coefficient because that will change it. So for the A's, we do have a radicand of A squared. The B's do not have a radicand. The C's do. So the C to the first power is inside of our radicand. And this will be our final answer. Again, this was just the letters, not the numbers. That's going to be in the next video.